Hey everyone, and welcome back to another ChemiVid. Today we will be talking about steady-state mass balances once again. So if you haven't seen steady-state mass balances number 1, I'll go ahead and link it in the box above. But I wanted to give you more practice with steady-state mass balances as they are a bread and butter skill for chemical engineers. So just to remind you about the steady-state mass balance, there's no accumulation that's going on, and you're going to take all the sum of the inlet mass flow streams and subtract them from the sum of the mass outlet flow streams. Remember that these have units of mass per time typically, and what we're going to be dealing with specifically today is a membrane separator. So last time we did a balance on a distillation column, this is another way to get separation. And essentially you have this membrane here, and it's going to selectively choose certain molecules over others. So you can see here on this left side, we have 5 of these red atoms, molecules, whatever you'd like to call them. Whereas on this right side, we only have 2. So it's selecting for these small blue ones to be pushed across the membrane. And it's a relatively effective way of separating things. So continuing on, let's just move straight into the example. We have this system. We have 2 separators, and these are both membrane separators. And what we're trying to do is we're going to get air, and air is made up of oxygen and nitrogen, and we're trying to separate the oxygen from the nitrogen. And we're going to do this through a series of membrane separators. You can see here we have air coming in stream 1. In stream 2, we're going to have something coming out. In stream 3, we're going to have something coming out. But you can see in the second separator, in stream 4, we're going to have 99% pure oxygen coming out. And in the bottom of the separator, we're going to have 99% pure nitrogen coming out. So we have 2 objectives for this system. One is to determine the mass flow rate and the composition of stream 2, which you can see right here we don't know anything about, okay? And we want to suggest improvements for the system. So I think you'll see as we continue on with this problem, there are some definite improvements that need to be made, and what would those be? So let's go ahead and get started. The first thing, as you remember from the previous video, is to draw a control volume. And so there are really 2 ways to approach this problem, and we're going to approach it both ways. Let's draw a control volume around each separator. So that's my control volume around separator 1. Here's my control volume around separator 2. Now, this first separator, I'm just going to call separator 1, separator 2. Separator 1, we don't know anything about the outlet streams, and so it's going to be hard to do an analysis on that one. But separator 2, we know a lot about. We know about stream 4, we know everything about stream 5, so that means we can figure out everything about stream 3. So let's go ahead and do an overall mass balance just to figure out how much mass is coming into that separator. So we know that our mass balance is going to be 0 is equal to the sum of the inlets, which there's only one inlet, mass flow rate of 3. And we'll subtract off the sum of the outlets, which is the mass flow rate of 4 and the mass flow rate of 5. And it's really just as easy as saying that the mass flow rate of 3 is going to be the sum of those 2. And it makes sense. Whatever comes in has to come out, and vice versa. So if you plug in those numbers, you get mass flow rate of 4 is 10 kilograms per hour, and the mass flow rate of 5 is 75 kilograms per hour. So we know that the mass flow rate of stream 3 is 85 kilograms per hour. Pretty simple. Now we can do the same thing, but do a mass balance on, let's say, oxygen. So we don't know how much oxygen, what the concentration and composition is here, but we can figure it out using a mass balance on oxygen in streams 4 and 5. So it's going to look really similar to what we did right here, just with the species. So we know that we're going to have the mass flow rate, or the mass fraction of oxygen in stream 3 times the mass flow rate of 3, minus the quantity, the mass fraction of oxygen in stream 4 times the mass flow rate of stream 4, plus the mass fraction of oxygen in stream 5 times the mass flow rate of stream 5. Very simple, very easy. The variable we're looking for in the end when we plug everything in is this mass fraction. We want to know the concentration. So I'm going to assume that you can do the algebra. Now that's not really an issue. And we're just going to give you the answer that the mass fraction of oxygen in stream 3 is equal to 0.125. So you can work through the math and make sure that you get that answer, but for the sake of this video, we're just going to be setting up the balances. So now we know everything about this stream, right? Balance of everything that's in stream 3 is nitrogen, and that means we know everything about stream 3 now. So I'm just going to write this up here in red because we know it now. This is 85 kilograms per hour, and we know that it has a concentration of oxygen of 0.125. So now that we know about streams 1 and 3, we can do a balance around separator 1 to find out about stream 2. So let's go ahead and do that. So this will be a balance on separator 1. So we can do an overall balance again, where we say that the 0 is equal to the mass flow rate of stream 1, which is coming in, minus the mass flow rate of stream 2 plus the mass flow rate of stream 3, because that's what's coming out. Plugging in the numbers, you can get that the mass flow rate of stream 2 is 415 kilograms per hour. Quite simple. And you can do another species balance around here to get the concentration, and it's going to be set up exactly like we have it here, just with the proper stream numbers placed in. So when you do that, you'll get that the concentration of oxygen in stream 2 is actually equal to 0.251. Okay, and now we have all of the streams defined. We know the mass flow rates of each stream, and we know the concentrations in each stream. So here comes the interesting part. I said there were two ways to approach this problem. We had to go through two different systems to do that. However, what if my control volume was just a little bit bigger? What if instead of drawing it around each individual separator, I drew it around everything, like you're seeing here? So I just skip out on analyzing stream 3 at all. You can see then my inlet streams, when I do it that way, become stream 1, and everything else is an outlet stream. Outlet streams are now streams 2, stream 4, and stream 5, and we don't even have to consider stream 3. This is the quicker way to do this problem, and if you work through it the same way, where you do an overall mass balance to get the overall mass flow rate, you will get 415, and you will get the same mole fraction of 0.251 in stream 2. So we're done. We've done the mass flow analysis, and we've done it in two different ways. And you can see that one way was definitely easier than the other. Typically in processes, we don't necessarily care about these in-between streams, especially because these look like streams 2, stream 4, and stream 5 all the way down here look like they're going to be pulled off as product, okay? Now, there are some times where you do want to understand what this in-between stream is doing and what its concentration is, if you're just looking at maybe separator 2 isolated. So really, it depends on the application, but for speed and accuracy, I think the overall doing both separators kind of lumped together is a little bit easier. So now we're supposed to make suggestions on improvement on the system. Well, something that was weird to me when I looked at this system is the fact that we are only taking in stream 3 85 kilograms per hour into a second separator. That doesn't seem like a lot. In fact, we are taking 85 kilograms per hour and we put in 500 kilograms per hour. That means we're only taking 17% of our inlet product and reprocessing it. The other stuff is just coming off at only a slightly higher purity. So something interesting to compare as well is in stream 1, by mass fractions, my mass fraction of O2 is equal to 0.23. But when I get to stream 2, my mass fraction of O2 is 0.25. It barely increased. And so this seems sort of like an inefficient process. To me, it would make more sense to take stream 2 and feed that into a second separator, as opposed to taking 17% of my inlet and basically throwing away the other 83%. So that's it for this video. I hope you understand a little bit more about steady-state mass balances, especially around multi-unit systems.